Hello, we've got part two of the 3D vector series that I'm putting together, looking at some IBHL math questions that were compiled by the authors of the Cambridge textbook. And in part two, we're going to explore what happens when we take two vectors, add them together where we scale one of the vectors. It turns out that if you take any two vectors, where you take a vector plus a scalar, we can make that sum, that new vector, go in any direction we want. And so in this case, they're claiming the direction we want to go in is 3, 2, 3. As in the previous video, I thought it was worthwhile to have a 3D rendering here, where we can see kind of what's going on. This black vector is our target direction, and the red and blue vectors represent the two given vectors A and B. What this figure is showing is if I just added vectors A and B as is, I would get this new black vector right in here. And what we can see is it's headed off in the wrong direction for sure. But if I were to keep adding a bunch of A's and a bunch of B's together, or that is to say, if I keep trying to head off in this direction, I'm always going to be going away from my target. So just from understanding these vectors, I'm expecting that my scalar here is probably going to be negative, which means this black vector is going to go back in this direction through the bottom of the plane and be still parallel to the given direction vector. So that's just based on the 3D rendering. I'm trying to understand the question before I dive in and answer it. So that's what these notations are trying to say. So that's where I got the idea that the scalar p that we're looking for must be negative, and that would give us then, if we had a negative scalar added, we can see we can head off in this direction, and all we have to do is adjust our scalar p a little bit, and it will tilt this so that it's going in the right direction. That's the plan. Now, the other thing here is the sum of A and B looks to be much longer than the direction vector I'm looking for. So we have two different things to deal with here, and the first is that we need to figure out what P is, and I kind of ascertained from the picture that it's probably going to be negative, but we still are going to end up with a vector that's probably longer than the vector that was given to us, the direction vector. So what we need to do when we set up an equation here is understand that the sum of vectors A and B, where we add a scalar or multiply a scalar to B, is going to be in the direction, but it'll have to be probably a scaled up version of the original given vector. So this is the key to setting up this problem and making us able to, find an actual reasonable solution. So here's the setup. Here's vector A, here's vector B, the scalar P, and the scalar K. P is our goal or target, and K is going to be an adjustment scalar that makes it so that we can be in the right direction and not have to be, exactly the same length. So, adding up the components separately, we get three equations with two unknowns, which is a nice favorable system condition to have. And in fact, one of the unknowns gives us a direct proportional relationship between P and K. P is always going to be twice the K value, or K is always going to be half the P value, however we want to slice it. So I could take the above equation, which is the same as the below equation, substitute in my half P, and find that P has to be negative 4/3. That's good news because I knew P was supposed to be negative, and we could see that here the given direction vector 3, 2, 3, if I take my scalar, substitute it into here, and add them up, I get this vector down here, so you can see it's going in the opposite direction. To verify that that is indeed in the correct direction, I first substitute the value that I found for P into the sum of my two vectors, and I end up with negative 2, negative 4/3, negative 2. And all I have to do is show that that is indeed parallel. Now, the way I did it was I just happened to notice that K is going to equal negative 3/2, because if we put P in for here, we get K equals negative 3/2. If we take that K value, multiply it in, we do in fact get the right direction vector. The other way we could have done this was we could have factored out whatever was required from here to make that equal there. It's all the same kind of thinking. It depends on which direction you're thinking. So that's enough evidence to support my work. That deals with, again, another 3D vector algebra problem. In the next installment, we're going to take this another step further, oops, forgot how to use my machine here. What we're going to do is do the same kind of problem, it appears, because we have two vectors. We're going to add them together with a scalar and get them parallel to another vector. What makes this one different is the direction of vector B is unknown. There's two constants, or there's the constant q in here. That's different from the problem that we did recently, or in this video. So stay tuned.